Imagine stepping onto a waterfall, not knowing it's there. And the moment your foot crosses an invisible line, there is no swimming back, no rope to grab, no second chance. Welcome back to the Cosmos in 5. Last episode we talked about black holes. Today we go one step closer to the boundary that defines them, the event horizon. What is the event horizon? The event horizon is not a physical surface. You can't touch it, stand on it, or even see it clearly. It is simply a mathematical boundary, a threshold in space around a black hole beyond which nothing, not matter, not radiation, not even light can even return. The name itself says it all. It's the horizon of events. Once you cross it, whatever happens to you is forever beyond the knowledge of the rest of the universe. Think of it like the edge of the observable universe. The universe is expanding so fast that light from certain galaxies will never reach us. Those galaxies are beyond our cosmic horizon. The event horizon works similarly but in reverse. Instead of light struggling to reach us from far away, light inside the event horizon struggles to escape a gravity well and loses. The map, Schwarzschild radius. In 1916, just weeks after Einstein published his general theory of relativity, a German physicist named Karl Schwarzschild solved Einstein equations from the trenches of World War I, no less, and discovered something extraordinary. Every object has a radius. If you compress that object below that radius, gravity would become so overwhelming that not even light could escape. The critical radius is called the Schwarzschild radius, and the sphere it describes is the event horizon. For the Earth, the radius is about 9 millimeters, roughly the size of a marble. For the Sun, it's about 3 kilometers. Our Sun isn't dense enough to collapse into a black hole naturally, but if you somehow squeezed it down to that size, it would become one. The size of the event horizon grows with the mass of the black hole. The supermassive black hole in galaxy M87 has an event horizon wider than our entire solar system. What happens if you cross it? Here is where it gets philosophically strange. If you were falling into a black hole feet first, you would not feel a jolt as you cross the event horizon. In fact, for a large enough black hole, you might not notice anything at all at the moment of crossing. The event horizon is not a wall, it's an invisible line. The horror would come later. As you fell deeper and the tidal forces, the difference in gravity between your head and your feet grew so extreme that you would be stretched like spaghetti. Physicists actually call this process spaghettification. That's a real scientific term. But here is the twist from an outside observer's perspective. If someone watched you fall toward a black hole, they would never see you cross the event horizon. Due to gravitational time dilation, the slowing of time near massive objects predicted by Einstein, they would see you slow down, freeze, and gradually fade away, your image redshifting into invisibility. To them, you would hover forever at the edge. The information paradox. The event horizon sits at the center of one of the biggest unsolved problems in physics, the black hole information paradox. The laws of quantum mechanics say that information cannot be destroyed. But everything that crosses the event horizon seems to vanish forever. Stephen Hawking spent decades wrestling with this paradox. He suggested that black holes slowly radiate energy, now called Hawking radiation, and might eventually evaporate. But where does all the information about what fell in go? Physicists are still arguing about this today. So here is the question I want to leave you with. If crossing the event horizon looks completely normal to the person falling in but means certain death, can you really say there is a line between safe and doomed? And if you can't feel or see the boundary, does it even exist in any meaningful sense? Think about it, and I will see you in the next episode.